Thank you for giving me the opportunity to come and talk to you about some of my research. I'm going to talk to you about some of the work that I've been doing throughout my PhD. So my talk is called HPC in Action, Uranium Bonding and the Nuclear Waste Problem. So just a brief outline. I've performed calculations over the past 3 years or so to simulate the electronic structure of molecules that contain uranium. From these calculations, we can derive various molecular properties. We can characterize the kind of bonds that uranium forms with other atoms in certain molecules. And the overall aim of this is that we want to see if we can work out why some molecules will bind selectively to some atoms and not others. Okay, so the broad context of my research is the management of spent nuclear fuel. So nuclear power currently accounts for about 11% of energy generated worldwide, or at least had in 2012, according to the Nuclear Energy Institute. About 2,000 to 2,300 tons of waste are generated every year, which, again, it might be less than some people expect, but it's still quite a lot, considering that some of this waste will be hanging around for a very long time. Over the coming decades, this is only likely to increase. There are very good reasons why nuclear power can and should maybe become more widespread to fill the gap that we need to meet energy demands, including that little picture there, which I think it's probably too small to see, will show the fuel energy density in uranium compared to, say, oil and gas. Unfortunately, the more energy we generate with nuclear power, the more waste we have to deal with. And this is, or at least some components of it, are extremely long-lived, radioactive, very toxic, generally quite nasty. I don't think anyone's going to disagree with that. And the current management solutions that we have for dealing with these aren't ideal. So this is the periodic table, which I hope everyone's at least a little bit familiar with. I've aimed my talk at quite a general audience. I've tried not to assume too much background knowledge, so I hope that people aren't either finding this too easy or really, really confusing. So outlined here in red, I've got the F block, the actinide series, and lanthanide series there. So these are the These are the elements that are... Sorry. These are the elements that are most interesting to us when thinking about spent nuclear fuel, particularly these ones ringed in green here. We've got uranium, neptunium, plutonium, americium, and curium. Right, so after a nuclear fuel cycle, we have some waste, and most of this is going to be unfissioned uranium, some plutonium and neptunium. We'll have some fission products, which are mainly going to be transition metals and lanthanides. And then we'll have small amounts of the minor actinides, so americium and curium. And these have half-lives of a few hundred to about 16 million years, so that they will be hanging around for a very long time. So I'll briefly just explain how these things are made in a standard fission reactor. So the diagram at the top is, I think, the one that most people will be most familiar with thinking about nuclear fission. You have a neutron come into the uranium atom and be absorbed by the uranium atom, which then splits into two approximately equal parts. These will probably be lanthanides or transition metals, releasing lots of energy and some more neutrons to go off and make more fissions. The minor actinides, like americium, are created through a slightly more complicated looking process where we have that neutron coming in, but then the uranium atom decays via another means to neptunium and decays again to plutonium, where it absorbs some more neutrons and then undergoes one final decay to americium. So we end up with tiny, tiny amounts of americium and curium. But as I said before, it's the length of time that these are going to be hanging around for that makes them a problem. So what do we do with it? So we can store it. We can stick it in drums and pools and leave it for our grandchildren to sort out. Quite a lot of waste is stored at Selective these days. Obviously, this isn't an ideal or permanent solution. storage canisters have been observed to bulge and corrode over decades, and there's always a risk that an accident or natural disaster will result in radiation being released into the environment. So another option is to bury it. So this picture here shows roughly how deep it would be buried compared to these lines at the top, which are the depth of the London Underground lines. So there's pros and cons to this. I mean, it gets it out of the way, at least for the time being. It would be buried in very, very specialised sites, so very deep, very stable geologically, no porous rock where anything could leak into the water table. But again, it's going to be there for millions of years, so we need to be sure that nothing's going to change in that time. So we come to reprocessing, whereby we reuse as much as possible of the nuclear waste using different types of reactor. We can minimise the volume of high-level waste that needs to be stored long-term. And we can also potentially transmutate long-lived species via neutron bombardment into isotopes which can then be used again or which will decay more quickly. So if we can separate the nuclear waste into its constituent parts, we can take out the uranium and plutonium. And uranium can be re-enriched and can go through another nuclear fuel cycle. There are pretty efficient means to do this, and this is actually already done. So a lot of uranium that comes out of a nuclear fuel cycle can then be re-enriched and go back in, and that happens already. So I'll mention here that where I've used uranium in my calculations, I've used it just as a model system for the later actinides, and I'll explain why that is later. So I mentioned transmutation, which is bombarding the minor actinides with neutrons, which induces further decay into shorter-lived species or into something potentially which can then go back into a nuclear reactor. And the problem with this is that after you've removed the uranium and plutonium, you're left with a mess of lanthanides and actinides, minor actinides. And lanthanides will shut down the transmutation process because they absorb neutrons very, very easily. So clearly what we need to do is separate those out as well. And the challenge here is that minor actinides and lanthanides are very, very chemically similar. And we need to design a system to selectively bind the actinides and leave the lanthanides where they are. There are some molecular systems which have already been observed to do this, like this one here. But we don't fully understand the process behind this, so it's difficult to improve it in a systematic way. So there are lots of reasons to do this kind of work computationally. So obviously handling radioactive material can be expensive and difficult. It requires highly specialized facilities. Computationally, we've got the option of exploring lots of different systems at the same time and looking at properties which might be difficult to measure experimentally. And there's always the option, if we come across something interesting, then that's a future target for a synthetic scientist to maybe look at our ligand system and see if they can make it. So I mentioned selective extraction. So for selective bonding, we need to control the way that atoms bond to one another. So everyone will have learned in chemistry at school that there are two types of bonds: a covalent interaction where two atoms share electrons, and an ionic interaction where an electron is donated from one atom to another. As with most things in real life, it's a bit more complicated, and most bonds fall on a spectrum between covalent and ionic. We've got quite a lot of evidence that actinides form bonds with a higher degree of covalency than lanthanides. And so what we're thinking is that we can maybe capitalize on this by designing a separation agent that maximizes the amount of covalency and so preferentially binds to actinides instead of lanthanides. So I'll mention electronic structure calculations. So all molecules have preferred conformations, which is a consequence of their electronic structure and which obeys the laws of quantum mechanics. And I've got some examples of well-known molecules there. The labels haven't come out very well, I'm afraid, but we've got water, methane, and ethanol there. So you can see that they do have a preferred shape that they like to be in. We can predict this structure with calculations. So we need to solve the Schrödinger equation. This one, that one there, which gives us the energy of the system as a starting point for any of these calculations, where the symbol psi is a wave function that describes the electronic structure. It looks like quite a simple calculation. Unfortunately, it's not. So even for simple molecules, we have to take into account the way that the atomic nuclei interact with each other, the way that the atomic nuclei interact with the electrons, the way that all of the electrons interact with each other. So even for a very small molecule, it's impractically large. But we make a series of approximations. I'm not going to go into what they are. I've done my work using density functional theory, which is just a way of approximating lots of these different things and predict the structure, again, of these molecules to a high degree of accuracy. So moving on to some more complicated systems, and this is some of the work that I've done during my PhD. First of all, my supervisor and I looked at some simple uranyl complexes. So uranyl is a uranium atom with 2 oxygen atoms. It's this thing in the middle here. So I've used uranium as a model for other actinides because we expect that covalency will be highest and easiest to spot here. And I've looked at a range of complexes of uranyl with these different ligands here, just small, simple molecules or ions binding to the central methyl atom, which is uranium in this case. And one of the things we modeled is the way that the bonds vibrate when they're exposed to light. So this can be used we can compare these values to experimental data where it's available and use it to tell us broadly whether or not our methods are roughly correct. Particularly for uranyl, there's 2 very well-known vibrations where the oxygen atoms will move up and down, either in sync with each other or against each other. And we can compare those to experimental data where it's available, and we can also use them almost like little antennae to probe other things that are going on in the molecule, because the frequencies of those vibrations depend on various other characteristics. So here are a couple of graphs from a paper we published last year. And what we've done is plot the frequency of these vibrations against a measure of covalency in the uranium ligand bonds. And we've got a nice strong correlation, which shows that they can be used as probes of covalency. We've also plotted this measure of covalency against a measure of stability. Again, we've got a nice strong correlation to show that, or at least suggest that covalency is, enhanced covalency is not a bad place to be looking for a selective ligand. So what we did next was move on to some more realistic separation ligands. So the one on the left, the one on, hang on, no, your left, my right, is BTP. This is a separation ligand that's known experimentally to bind to actinides over lanthanides. And the ligand that we were interested in is isoamethrin, this one here. So we found that the bonding in these 2 complexes is actually very, very similar, which is interesting because this one, isoamethrin, comes from a family of ligands that are very easy to modify in lots of different ways, which makes it a good candidate to see to what extent and how easily we can tune a ligand to increase covalency. So that's what I did next. I increased and decreased the size of the ring by adding and removing carbon atoms to create these 4 different systems here. And then I looked at and characterized the uranium ligand bonding. And I've got this graph here. It's not quite as nice a relationship as in the previous graphs, but there is a relationship between the measure of covalency in the uranium ligand bonds and the stability of the molecules. So as there is more covalency in the uranium ligand bond, the molecule becomes more stable, which is good news, at least initially, to suggest that we're not completely barking up the wrong tree. I'll give you some conclusions. I've talked about some of the work that I've done over the last few years. We've come across evidence for a strong relationship between covalent character in uranium ligand bonds and stability. We've shown that uranyl undergoes predictable changes when these bonds form, and these changes are related to the amount of electron sharing or covalency in uranium ligand bonds. There are strong similarities between an isoamethrin ligand and the industrially useful BTP ligand, there's evidence that covalent character in the uranium ligand bonds of uranyl hexafluorines can be controlled by modifying the ligand by increasing or decreasing the ring size. And there's some quite promising results so far. So the future, this graph here is projected world energy consumption over the next 15 years, I think, to 2030. And as you can see, it's continuing to rise quite sharply. So as global energy demands rise, somehow we need to fill the gap. There's a lot of reasons why nuclear power is a good candidate for doing so, at least as a stopgap measure. But the more energy we generate this way, the more waste we have to deal with. And although we're a long way off, an ideal solution would shrink the volume of high-level waste, so the minor actinides, down to a very small amount, so to reduce the amount that we need to store for long term. And hopefully theorists working together with experimental and industrial scientists can take steps towards achieving this goal. And facilities like GRACE, like Legion, that allow us to explore the theory behind stability and covalency and selectivity can definitely help with this. So thank you all very much for listening. So thank you to all of these people here. And any questions? Thank you.